Hello from my side. My name is Sebastian Steinbus, CTO and lead architect of the International Data Spaces Association. And you just saw the 3 of the pilots that we do have in the MIDIH project. And I'm going into the details of one of the industrial pilots that was driven by IDSA and the IDSA partners in the MIDIH project. And it's in the steel domain. So please move to the next slide. Thank you. So what drove us when we started a use case, an industrial experimentation in the steel sector, where we see that the variety of steel components still increases. And this is not only in the steel production, it is in every other manufacturing industry the same. And one implication of this is that the supply chains become more and more dynamic. They have to be adapted to new situations, to new suppliers, or to new customers, and so on and so forth. And this is something that is special about the steel supply chain, is that more and more 3D printing services are available also for metal parts. And they are reliable, they are usable, and they open a new playing field. And it's a little bit innovative, and things change here a little bit because these supply chains are more and more dynamic. But again, this applies to every other manufacturing scenario as well. So please go to the next slide. We had one example in our experimentation, and this was the valve box. You can see on the left side. It's a valve box for submarines, and as you can see, it's a box. But if you produce it or engineer it with additive manufacturing, you can explore completely new geometries. And you see it in the middle. It looks a little bit differently, a little bit more organic, and it's more expensive, but it's more reliable. And so in submarines, it's a good idea to use those valve boxes produced with an additive manufacturing. But those submarines are typically produced all over the world. The one you can see on the right is produced in Singapore and produced by ThyssenKrupp in Singapore. So what you can do within additive manufacturing, you can produce the part where it's needed. That reduces the amount for logistics, the travel venues that you have for the logistics of your part. You can produce it everywhere, but at the same time, the data is becoming more and more important because there is a lot of engineering know-how to make such a valve box to such an organic shaped thing, and you have to protect this IP. And this IP is completely into data. If you give away the data, the description, the CID file of such a part, every printer can print it again and again and again without paying any license fee. And within the IDS approach, we can protect this IP, the data that is inside there. And I will go into the details of that. So please go to the next slide. The idea of IDS is not to provide the new huge platform for everything, the single cloud system that stores every data set and provides access control to this. But we are aware that there are a lot of systems that are being combined to an ecosystem, here to an additive manufacturing ecosystem, including a logistics system for the supply chain of additive manufacturing. And the idea of the IDS is to connect all those different platforms that are in use and required or necessary to fulfill this business. The IDS connects all those different platforms and all those different systems in the printing hubs, in non-destructive testing, in post-processing like deburring or painting. They connect them, and we can put data usage constraints on top of the data. So, for example, if the engineering company, in this case ThyssenKrupp, provides the data set, the CID file that has to be printed to a printing hub, they can put a usage policy, a usage constraint on top of this data and state you may only print it once or 3 times, whatever. And the same also applies to a logistics company that can say, I can transfer part A from company A to company B in this time and for this amount of money, and you may see it, but you may not show this data to other logistic companies to make a benchmark or something like this. And this is what we can do. We can bring together all those different systems and combine them to one huge ecosystem that is more dynamic and more flexible. On the next slide, please, there is a little bit more a technical view on what we've done so far. In IDS, we make use of the so-called IDS connector. One important artifact that is a trustworthy runtime, a platform inside a company, for example, that enables the data exchange. And the IDS connectors in the different companies, here on the right side you can see the print hub, on the left side you can see the engineering part, ThyssenKrupp side. Both systems exchange the data, the CID files if necessary. For example, in the first stage of such a process, when the companies are asked to make a price or a timing, create an offer, when and how to create this part. The CID file gets provided to the print hub. They can see it and create an offer on top of this. And then there is a selection phase. We have a number of different offerings, and then there is a selection process. We select one of those offers, and then all the other companies, all the other print hubs are not enabled anymore to see the files, and more files with more details are provided to the print hub that was selected. This is supported by a blockchain node, by a blockchain system based on smart contracts to provide access or no access to those different files. In this scenario, on the lower right side, you can see the client, the customer. The customer is in this scenario not yet connected to the IDS, but in a further stage, we will also connect the customer, the client, and also others. And I would like to show you how this works on the next slide, exactly. So this is the basic idea between the information flow and the material flow in such an ecosystem. There is a customer that maybe just has a sketch or an idea what he needs. For example, I need a valve box for a submarine. And of course, for this scenario, we need systems, ecosystem enabling, finding connectivity, accessibility of data, interoperability, and usability of the data assets. And then there is something like a marketplace that is also built in other projects where you can compose different kind of services. I need engineering services from this company. I need consultancy services from another company. I need a printing hub. I need material supply. You can compose your service as a customer. Which different participants or which different suppliers or partners do you need? And then, of course, the first and one of the important steps is the engineering part. So there is a sketch of a part, and an engineering company with a lot of knowledge in additive manufacturing engineering creates a digital representation based on the requirements that were stated. And in this CID file, as already said, there is a lot of intellectual property inside, and it has to be protected because it can be copied as often as you want it. Some of you remember those Netstar times when music was copied as often as wanted, and this was a huge problem for the music industry in those days. Today, we have the same things, but only in manufacturing industries. So, but the information based on the engineering part. So, what kind of material do we need? Which capabilities does a 3D printer has to have? Which post-processing services are necessary? And what requirements do I have with regards to non-destructive testing? They can all be stated and then distributed with usage policies on top to all the partners. And this service network, the service ecosystem can be composed, orchestrated, and executed then afterwards. And if we move through the material flow from the supply to the 3D printing step to the post-processing services, as said, deburring, painting, and then in the last one, non-destructive testing, a lot of data is generated. And typically, it would be good if all this data would be available to everyone, but also based on access control and based on usage policies. So who can see which data for the part, but also the same applies for the supply chain, because this supply chain is then really flexible and dynamic. You can print the parts in different printing hubs, choose different post-processing service providers, different testing facilities, and every time the supply chain is differently. So you have to exchange the data and ask for offerings from every logistics company, and then create the best, the optimized scenario for the supply chain. And therefore, you need the data of all the logistics providers, of different companies that provide logistics services. And then you can optimize this, make a benchmark. And you can optimize this with regards, for example, for the cheapest setting. the cheapest printing hub, the cheapest transport, and so on and so forth. And maybe this doesn't fit to your estimated time of arrival. I need this part in a week, and the cheapest part might be in 3 weeks. Or you can optimize this with regards to the estimated time of arrival. You can optimize this that the part is exactly at that point of time there when it has to be put into the submarine. Or, for example, think about your carbon footprint. You have to optimize with regards to your carbon footprint. So the part should not fly, maybe, but may be transported via train. All those things we can is based on data, and we have to bring together this kind of data into a digital or virtual data set to optimize this. And then the most important and most promising part is that we can collect all those different data from the different data sources. We have the sensor data from the printing hubs. We have a lot of information, material information from the material supply. We have details from the post-processing service and from the non-destructive testing. And not every participant in this ecosystem should see all the data for different kind of reasons. But what you do have is really a big digital twin of your part, of this valve box that was printed. You have this digital twin and can put new business models on top of this. For example, if you would only have all this data and you would only have a cool algorithm, you can ask the part later on, will you take this force? Typically in steel we talk about standards. This part will take a force of 100 newtons and then it will fail. But you can ask the part, will you take a force of 120 newtons for half an hour? Because I have 2 machines and one fails, I have to shift my workload. And the part could say, based on this data and the cool algorithm, yes, I will take the force, but you have to exchange me not in a week, but in 3 days. And these are real cool new business models that are enabled by data and by the availability, the sharing of data. This is a use case that we are working in MIDIH, and together with ThyssenKrupp and the MIDIH partners. But there are other use cases that we can connect now to this use case to enlarge this ecosystem. And if we move to the next slide, I have another example, the Smart Factory Web. The Smart Factory Web is an IIC testbed that is now also using IDS technology and the asset administration shell from the platform Industry 4.0. So it can be easily connected to this ecosystem. And here the question is, I have a factory and I need more production lines because my factory is running with full capacity, with customer orders, or one of my machines failed. So how can I scale out? And I have a web of different companies, different factories that provide similar services. I can easily scale out to another factory. Ask my competitor, please produce me these parts for my customers. And if my factory is not running under full capacity, I can also produce for my customer, for my competitors, other parts. So technically, we can support this, but this will only work if we can put usage policies, usage conditions on top of the data. Because I don't want to share my IP. My IP has to be protected. My customer data has to be protected. But I want to make use of this web. And we're integrating, or we have integrated, the Smart Factory Web within IDS. Please go to the next slide. So what basically happens there is that there is an asset registration process that every asset and machine, for example, a 3D printer is registered in the Smart Factory Web, and it can be searched. You can search via the capabilities of the system, what kind of system you do need, and then you can negotiate with a factory network. Say, okay, I want to produce this part, but what is the price? What is the delivery time? What quantity do you need? And what quality do you need? And so on and so forth. And then you can do the ordering, operate things, manufacture it, and monitor what happens. And all those steps are completely based on data and make use of the machines in behind. And then my final slide, you can see that one important thing is here, that we have to cross different borders, company borders. We are not inside one security domain anymore, but there is a collaboration of different companies, of different systems, and technically speaking, of different security domains. And the IDS connector bridges between those different security domains, between an ERP system in one company, the manufacturing company that produces something, and the smart factory lab controller on top of this. And of course, we have to integrate different kind of standards here. IDS is for the data exchange, for data sharing, crossing the security domains. Of course, we have to integrate standards like the asset administration shell from the platform industry 4.0 or OPC-UA, for example. And we are combining this to really create a manufacturing ecosystem where new cool business models can be executed there. Yeah. That was my part, and I'm happy to give the word to the next one. And I'm not sure who it is. I think it's Martin and Liz M, if I'm not mistaken.